Most people think the alternator only charges the battery. That's wrong. In a running forklift, the alternator isn't just topping off the battery, it's the real-time power plant for the entire machine. Once the engine is running, the alternator supplies power to your dash, solenoids, safety circuits, lights, and the fuel system, everything electrical. The battery? That becomes storage and stabilization. If your forklift dims the lights when you lift a load, if it shuts off randomly at idle, if you're replacing batteries more than you should, you're not dealing with a battery problem. You're dealing with how the alternator behaves under load. And to understand that, we need to understand how it actually works. Hello everyone, welcome back to the Lift Parts Warehouse channel. In this video, we are discussing yet another important part of your forklift, the alternators. Every alternator is based on a fundamental concept, electromagnetic induction. Back in the 1800s, Michael Faraday discovered something powerful. If you move a magnetic field across a conductor, you create voltage. Not by magic, not by chemicals, by motion. When a magnetic field cuts across copper windings, it forces electrons to move. That movement is electricity. And here's what matters. The faster the magnetic field changes, the more voltage you create. The stronger the magnetic field, the more output you get. The more turns of copper wire, the greater the power produced. Now let's translate that into forklift terms. Your engine is spinning a magnetic field inside tightly wound copper coils. That spinning magnetic field is what generates electrical power while you're lifting pallets, steering, and idling in a warehouse. It's mechanical motion being converted directly into electrical energy. And that's just the beginning. Now that we understand electromagnetic induction, let's open the alternator up and look at what's actually happening inside. We'll follow the energy. When the engine is running, a belt turns the alternator pulley. That pulley spins the rotor shaft inside the alternator. Now inside that rotor, we have a field winding, copper wire wrapped around an iron core. When we apply a DC voltage to that winding, it becomes an electromagnet. That voltage comes in through slip rings and carbon brushes riding on the shaft. At startup, the battery supplies the initial voltage to the ignition circuit. That energizes the rotor. Once energized, the rotor becomes a rotating magnetic field. The finger-style pole pieces on the rotor create alternating north and south poles as it spins. No magnetism equals no output. So everything starts here. Now, surrounding that rotor is the stator. The stator doesn't move. It contains three separate sets of copper windings spaced 120 degrees apart. As the rotor spins, its magnetic field sweeps across those windings. This is exactly what Faraday described. A moving magnetic field cutting through a conductor induces voltage. Because the windings are spaced 120 degrees apart, the alternator produces three-phase AC power. Three-phase provides smoother output and better usable power than single-phase. But right now, it's still AC, and the forklift needs DC. Let's see how the real conversion happens next. At the rear of the alternator sits the rectifier bridge. In most designs, this uses 6 diodes. Each of the 3 stator phases connects to 2 diodes. Those diodes are arranged so that both halves of every AC cycle are used. That's called full-wave rectification. Instead of wasting half the wave, the rectifier converts the entire AC waveform into pulsating DC. It's not perfectly smooth. There are some ripples, but the battery helps absorb and stabilize them. If one of those diodes fails, the ripple increases and the output drops. That's when you start seeing flicker or unstable voltage under load. There's another smaller set of diodes inside called the diode trio. This circuit takes part of the stator's AC output, converts it to DC, and feeds it back into the rotor field. That means once the alternator is spinning and producing power, it can energize itself. It no longer depends fully on the ignition feed from the battery. That's what makes it self-exciting after startup. If the diode trio fails, the rotor may not get proper field current and the alternator won't sustain charging. It may spin, but the output won't build properly. Now the last major piece, the voltage regulator. The regulator constantly monitors system voltage. If the voltage rises too high, it reduces the current flowing into the rotor field. If the voltage drops, the field current increases. Modern regulators do this using high-speed transistor switching, turning the field circuit on and off rapidly to control magnetic strength. Stronger magnetic field equals more stator output. Weaker magnetic field equals less output. That's how the system maintains roughly 13.8 to 14.4 volts while the engine speed changes. And that's the full loop. Engine spins rotor. Rotor creates a magnetic field. Stator produces three-phase AC. Rectifier converts to DC. Diode trio feeds rotor. Regulator adjusts output. That's the alternator working in real time. Now, here's where forklifts differ. Everything we just explained applies to cars too. But forklifts operate under very different conditions, and that's why they stress alternators harder. Forklifts spend a lot of time running at low RPM, sitting in a warehouse, waiting, and lifting at idle. Every time you lift, tilt, or side shift, solenoids energize. Electrical load instantly increases. They lift heavy loads at low RPM. They start and stop constantly. They run in enclosed engine bays with limited airflow. And they operate in dusty environments. That's hard on alternators. Now, picture this. An operator lifts a pallet at idle. Electrical demand jumps, hydraulic solenoids energize, system voltage dips slightly. The voltage regulator senses that drop and increases the field current to the rotor. Stronger field, higher stator output. But a stronger field also means more internal resistance, more current, and more heat. At the same time, mechanical load increases on the pulley and belt. So the alternator isn't just spinning, it's actively adjusting output in real time. Repeated low RPM load events generate heat, which is one of the biggest reasons forklift alternators fail earlier than automotive ones. Now, let's connect the theory to what actually fails in the shop. A bad diode increases ripple and causes unstable voltage. A failed regulator can overcharge and damage batteries. Worn brushes or slip rings weaken the field and reduce output under load. Heat in enclosed forklift bays accelerates it all. A belt slip or a weak exciter circuit can prevent proper charging altogether. Forklift duty cycles make these failures appear sooner than in cars. If you're replacing batteries repeatedly, stop and check the charging system. If the voltage looks fine at idle but drops under load, the alternator is weak. Suppose you see flickering lights or electronic instability. Suspect ripple from a rectifier issue. Diagnose the cause before replacing parts. Charging problems are often misdiagnosed as battery failures. Remember, the alternator is the electrical power plant while the engine is running. If it can't maintain output under heat and load, downtime follows. At Lift Parts Warehouse, we supply OEM spec alternators built for industrial forklifts of all makes and models. Visit our store now to order and avail same-day shipping. Keep the machine charging properly, and it will keep working. See you in the next video.